What's up, guys? It's Mr. Stark back here again, and I wanted to do an experiment on the multi-wire circuit. So part one of the video describes a pictorial picture on a whiteboard on what's going on with a multi-wire circuit. We actually talked about 210.4 A, B, C, and D, and now I have a picture or a working experiment of what can actually happen if you open the neutral in a multi-wire circuit. So if you remember the first video, you'd remember that this is here, and all I'm using this single pole switch for is to open the neutrals. So it's wired completely unconventional, but I wanted to show you what would happen if we open the neutral, and I figured putting it across a single pole switch is the easiest, safest way to do this. Now, if we remember anything about our series and parallel rules, the first thing we would remember is that right now this is a good working circuit. I have 120 volts up in this circuit, which could be the black circuit, and then I have 120 volts going down to this circuit, which could be the red circuit, on a multi-wire circuit. In the panel, we have both of these circuits tied onto, which should be a 2-pole 15, so I wanted to bring this to your attention. This is what's called a common handle tie. It's a listed handle tie. So if you don't have them across your circuit breakers, if you're missing this, you need to buy this if it's a multi-wire circuit, and simply insert it over the two circuit breakers like so, and then I could simultaneously disconnect both ungrounded conductors from the source, just like that. So now black is dead and red is dead. That's one of the provisions in 210.4 A, B, C, and D, is to simultaneously disconnect both ungrounded conductors at the same time. So we met that provision, we put that on, two circuits are both running. Let's just say this is the black circuit up on top and this is the red circuit up on top. Right now we've got two circuits that are operating, they're in parallel with each other. And if we remember our series and parallel rules, this will make more sense when we go through this experiment. So what I'm going to do is I'm going to open the neutral, and when I open that neutral, we're going to experience a voltage drop across this light bulb and this light bulb. And it's based on the resistance of each light bulb will determine how many volts I drop across each circuit, each load. So let's do that. Right now, I've got my meter set for voltage, and I'm going to open the neutral, and what I want you to notice is the brightness and the dimness of each circuit. As soon as I open this neutral, I create a series loop. I'm creating a series loop, and my source voltage here at this panel is actually 208 volts to ground. So 208 volts from hot to neutral or from hot to ground, that's the service that we have here. If it were residentially, it'd be 240 and your voltage drop would be a lot different. But for now, you're going to see exactly what's going to happen. When I open this neutral, I create a series loop across both ungrounded conductors, which means my total voltage in the circuit is now 208 or 212, whatever the service is. And I'm going to drop voltage across each of these resistors, and we're calling these light bulbs resistors. So here we go. Notice how that light bulb became very dim. This light bulb became extremely bright. I'm going to test for voltage across this, and we're going to see, based upon the resistance, how many volts we're dropping across this. So right now we're dropping 162 volts on that light bulb, when this is only designed to hold 120. So because voltage is additive in a series circuit, and if we start off with 208, we should conclude that we're in the 40-something volt range down here. So let's test this. Get that in there. And now let's look at my meter. There's our 47 volts, and obviously not enough voltage or pushing power to allow current to adequately flow and allow this light bulb to do what it's supposed to do. So we did this already in class. We did this through calculations of paper labs and all this, but why is this so important? Now think of this for a second. If my resistances were different across both of these circuits, it's going to affect indirectly how much voltage I drop across each of these circuits if I have an open neutral. So if I had a TV plugged into this top receptacle, and let's just put our meter in here so you can see again, I still have 162 volts dropped across that open neutral. So maybe I might blow up the TV or short something out in the TV because it's just operating on an over voltage. Whereas down here at the bottom, I'd be operating on under voltage. And once again, 47 volts on that circuit. So either scenario is a bad thing, because if I affect voltage, I then adversely affect current. So if we were to take this off and set this into my AC current, and if I was to test current across this load, I'm at 0.3 amps. So once again, this is a series loop, and the open neutral created that series loop. Current is the same everywhere inside of a series circuit. If I change it back, look what happened to the current. So right now we're back into a parallel mode. My current went up. So depending on the resistance, those numbers are affected as well. So up here, I opened up the neutral again. I'm testing for current on this loop, and we knew it was a series loop, so it had to be 0.3 because that's what it was. But now if I change it back to a normal circuit, we went down back to about 0.2. So your resistance or your load is directly going to be affected by what you do to that circuit. Now, if I want to send this point home even a little bit further, we could talk about 210.4. 210.4, A, B, and C says all circuits shall originate from the same panel board. So 210.4a, all circuits, which would be this is part of the multi-wire, shall originate from the same panel board, and they do. You can see that it's coming through this connector and from the same panel board, and we have that. We know that theory is involved if you took it from two different panel sources, because they have to come back on that neutral, and we want to make sure that we're on opposite phases in the panel when we do that. So that code is based upon theory that you get it right. The next thing in 210.4 is grouping. So grouping means that the neutral that is being shared between the two hot conductors is adequately labeled so that the person who comes in and maybe they demo a panel or upgrade or something, they know that that is a multi-wire circuit. In other words, there's two ways you can do this. You can go over to this conductor and maybe put numbers on it and say this neutral belongs to circuit 6 and 8. So 2, 4, 6, and 8. 6 and 8 would be the numbers in this panel. I could put a number 6 and a number 8 on that neutral. Or I could put a string tag, which is another type of label, around that cable that would let me know that that neutral belongs to those two hots. Or the other provision is if the connector or the fitting clearly identifies that cable as being grouped. This one does, because I've only got one cable that comes through that connector, which clearly means that neutral belongs to those two conductors. Where this could be a little bit confused is if all of these were in a raceway or a conduit, and I had a bunch of black reds and a bunch of whites, and they were coming through a conduit, I would need to then group them because that raceway doesn't clearly identify neutrals being grouped with their ungrounded conductors. The last provision, equally as important to all of the other ones, is that you're only to serve line to neutral loads. So this would be a line to neutral load, line to neutral load, and the exceptions are if it could be a line to line load as long as it's on a 2-pole breaker. This is the case of that anyways. So that meets the last rule, simultaneously disconnect all ungrounded conductors at the same time. And why is that important? Well, let's just pretend that these two circuits were tied on to circuit 20 or I'm sorry, to this circuit and this circuit. And I said, hey, you know what, go turn off circuit 10. Then I go into that junction box and I start messing around with it thinking that 10 is dead, but I'm actually getting current on this circuit, which is the one being shared with the neutral, and I go and open that splice up and I get hit pretty hard because this one is still carrying the current from the other circuit. Whereas if you put them both on a common handle tie or a 2-pole breaker, it simultaneously disconnects both circuits at the same time, which means if I only need circuit 6 turned off, well, I'm turning off circuit 8 too because it's a multi-wire, and I won't get current coming back on the neutral and hit me. Last thing I want to cover is, why do we care about an open neutral? Well, we can see the voltage drop could be substantial depending on the resistance. So let's take a look again. We open the neutral and we see that that got bright. It's taking a lot more voltage, and obviously the other circuit isn't getting enough voltage. When would this happen again? Maybe you'd be in a junction box, right? And you're tapping onto a circuit and you're doing it live. And you start splicing that neutral onto all the other neutrals and you loosen that splice up, or maybe you took the wire nut off and there wasn't a mechanical splice in there. And that neutral it would be intermittent. It'd be like this. You're loosening that wire up. Same thing here. Maybe I'm in a panel that's completely full, right? The panel is full, all of these are full, and I don't have any more places to put a wire, and I violate the rule in the code book, 1 wire per terminal, which is in Article 110. 1 wire per terminal means unless this is listed for more than 1 wires, you can only put 1 wire under each terminal. Well, you go into a panel and they're full. And you're like, man, I can get 1 more. I know I can get 1 more wire under that terminal. All I gotta do is loosen this one up and then stick the other one under it, and we'll call it a day and nobody will know. Well, first of all, you're violating the code. And second of all, as soon as you loosen up that screw, you make this neutral loose and bounce around inside that hole. Bouncing around inside that hole is the same thing as doing this. See how I'm getting that voltage drop? I'm opening and closing the circuit inadvertently by loosening that wire. So you can cause an open neutral that way as well. Obviously, the most common way of causing an open neutral would just be bad workmanship and not knowing exactly what you're dealing with. But hopefully this video helps you to further understand the dangers of the multi-wire circuit. If you're running a 3-conductor and sharing a neutral, you have to be aware it's got to be tied on to a 2-pole circuit breaker. The wires have to be grouped as to which neutral belongs to which hots. They can only serve line to neutral loads. And more important than anything, out of all of that, if you can't meet those provisions, don't run a 3-conductor. Run 2 12-2s or 2 14-2s if you don't understand the rules of a multi-wire circuit. So hopefully the next video will show us plugging in a load like an old TV, and we're going to leave it on. So imagine a TV is being plugged into this receptacle, getting anywhere from 170 to 200 volts. I'll change that resistance on that circuit. It'll affect this voltage drop. And we'll see if the TV starts to smoke and catch on fire, which it will. And that's definitely the reason why we have to understand 210.4, A, B, C, and D are all based upon theory. So know your rules, know your code, and then you won't get it wrong. See you at the next video.